that if we are in that age, okay, this non-invariance of Maxwell's equation was very obvious. Okay, we will see that the Maxwell's equation are also invariant in any frame of reference, but this non-invariance arised, okay, during that time when the speed of light was c in any frame of reference was not yet proved. So that time it was like Maxwell's equation was not valid. So we have the four Maxwell's equation, and when the Galilean transformation was done, it was observed that it was non-invariant. The question is, what's the reason that it was considered to be non-invariant? Well, the reason was C. The reason was C. If we basically have a wave equation, which will be something like this, you do a bit of maths, a bit of algebra, and you'll get the wave equation to be this. And we see that there is a speed c involved, which is considered to be the speed of light. So when the values of permittivity and permeability was replaced, the c was calculated to be 3 into 10 to the power 8 meter per second. The problem was that is this value of c same in all media or only in a particular media? That was not yet answered, because if we look into the idea of relativity, we see that the velocity will be different in different frames of reference. So this is what we have seen in the last class. So that means if c is the speed of light, according to this relation, that should also be different. So at that time, even Maxwell didn't have the answer, and then they assumed that maybe it was true for a particular medium. Now the thing was, what is that medium? That medium was considered to be ether. So the question is, does it mean that the speed of light is different in different medium? Okay, the answer was not known at that time. Today we know it's not. Its speed of light is same in all the medium. So how? This is something which we are going to discuss in today's class. And who have discussed this? This was actually done by Michelson and Morley experiment. So we are going to understand theoretically after, of course, after doing some kind of derivation, that how does Michelson and Morley came to this conclusion that the speed of light will be actually same in any medium that you basically consider. Okay. So what we have to do here is we do usually have to write down a lot of statements. Okay. So I prefer writing down those statements, but itna kuch likhna hai aaj, so much theory. Rather prefer typing it. Okay. So what happened was like this. Okay. So you have to, whenever you are asked a question about Michelson Morley experiment, you have to write down a lot of statements. Okay, it's very important because it's a lot of theoretical assumptions that you have to write. Okay, so you have to explain it properly. That's very important. So it was assumed at that time, okay, that the speed, okay, of light is what, c meter per second. It was assumed to be c meter per second in only a frame, okay, where there is ether. So ether is a very important term. If there is ether, the speed of light would be actually c. Okay. Other frames, okay, may have c as different. So you have to just understand that this was actually an old thought. It is not something which has been assumed now. Okay, so these old thoughts, okay, maybe I will just write it down as old thoughts so that you are clear about it. Don't mix it up. Okay, it was assumed at that time, and today it may not be true. Okay, and we know in fact it's not true. Ether, okay, frame was considered to be the S frame. So we have already developed a good idea about what is an S frame and what is an S prime frame. And the Earth frame, okay, was considered to be the S prime frame. Okay, let's just assume this for now. This is important. And if we actually know now what are the frames, we can actually draw an image. Okay, now what do I mean by ether frame is the S frame and the Earth is the S dash frame or S prime frame. It is something like this. Okay, maybe I can do it here. Okay, imagine this is your ether frame. These lines actually are representing the ether frame. Okay, and I will, try to draw the earth. I don't have a circle tool here, but anyway, I'll just try to draw it. So this is okay. Your earth frame. So this is your earth frame. Okay, let's imagine. And this is the ether frame. So the earth is basically moving with a velocity, let's say v. Okay, and this is the earth frame, which is actually considered to be the s prime frame, and the ether frame is considered to be s. Okay, now understand this. This is, let's say, this blue circle is the earth. Now understand this, that the earth is moving in this direction with a velocity v, and maybe we are having, an event where we have the speed of light c. If the speed of light c is, in this ether frame, the speed is c, the question is, what will be the speed of this light when we are considering it in the earth frame? And let's say the earth is moving with a velocity v with respect to the ether frame or the s prime frame. S ray, right? So that is very important. So this is what was assumed, okay, at that time, and you have to understand it very clearly because it's a bit confusing. Let's just try to draw a image of whatever experimental setup was actually done by Michelson and Morley. Okay, so what I'm going to do is I'm going to draw an image, and for you also, you should actually be able to draw it during your, whenever asked, for explain the Michelson Morley experiment. So if a question comes, explain Michelson Morley experiment, this diagram would be important. Okay, so we do have, a splitter, you can say a glass slide or something like that, which basically splits the light. Okay, and we may have a mirror on this end. Okay, and another mirror was actually set up on this end. Okay, so these are all mirrors, so that means, it's going to reflect the light in total 100%. Okay, so these mirrors are there on both the sides, and we are naming it them as mirror 1 and mirror 2. So what is happening is you are actually having a signal, and as soon as it hits the glass plate, is going to get divided into, two parts. So let's say I basically have a light signal, okay, a light signal which comes in this direction. Okay, and let's just consider this part of the mirror. Okay, a part of this will actually be transmitted, okay, and go, okay, maybe I can do this, transmitted and go and hit this mirror. Okay, it might, get reflected also, but we are not considering this right now. For this moment, just imagine you have got a ray of light which is going, hitting the glass plate, and a part of it is getting transmitted and hitting the mirror M1. Now, as soon as it hits the mirror, a part of it will also get reflected back. So entirely it will get reflected back, not a part of it, because this is a totally silvered mirror, 100% reflection. So as soon as it reflects, it comes and hits back the glass plate, and then again a part of it will go down, right? So this is what is happening right now. Okay, after it hits the mirror, it comes back and, gets reflected downwards. And what we do downwards is we basically place a telescope there. We basically place a telescope there. That was the brilliance of, Michelson and Morley, and you will understand that what exactly they did, based on which they were able to say that the speed of light is same in any medium that you consider. You basically have the telescope here. Now, a part of it is transmitted and a part of it gets reflected upwards also. So let's say a part of it gets reflected upwards. Okay, so maybe I'll use a different color. So a part of it will also get reflected upwards. Okay, let me use a straight line. So this gets reflected upwards. So this is the direction right now. And that reflected light which comes from this mirror again comes down. Okay, and again, it gets transmitted. See, there will be other process like absorption, reflection, and so on, but we're just considering the transmitted beam. Again, a part of it will get transmitted, and that also will travel downwards and hit the telescope. Okay, now before I proceed with whatever sentences you need to write, I think this idea is already clear to you about interference and diffraction. If we have, two waves let's say the source is the same, so we know that the wavelength will more or less be the same, or the frequency will more or less be the same. The first wave, travels this much path, it goes here and comes back and goes to the telescope. The second wave will go up, reflect back, and then again come to the telescope. So there might be or might not be a path difference. Depending, okay, this is something which you have studied in wave optics. Depending on whether these waves will have a path difference, we will actually get a fringe pattern. Okay, so these waves will actually result in the formation of some kind of fringe pattern, right? So you might have, a dark line, and then maybe there is no light, darkness and light line, and then you'll get some light and again some darkness and so on. So you'll get these kind of fringe patterns when you look through the telescope. So the setup was made in that way during that time. Okay. Now the question is, what exactly they have done after doing the setup. So this setup was done. Okay, and I hope this is clear. So what we can do is, maybe I can just label this. When you write down for your exam, you have to label it out. That's very important. So this is mirror M1. Okay, and I will consider this as mirror M2. Just naming them. Okay, and this is basically a glass plate that we have. Okay, and let's imagine that this length is L, this length is L. Okay, so the transmitted light will travel a distance L and then it will come back. Okay, on here also we can consider the distance to be L. Okay, so what we are going to do now is going to analyze this mathematically. Okay, and let's just do it. Okay, right now. So I will need this image. So what I will do is I'll copy this image in the next slide, and I think that will be easy. We are going to do some mathematical calculations to this. Okay. Okay. So what we have is this. So we have this reflection, and we are going to analyze this mathematically. Now what we have seen in the last class is that the velocity, okay, the velocity, what was our velocity? Vx prime. So please remember, x prime is the Earth's frame. So I want to observe what is happening from the Earth's frame in the ether frame. Okay, so this relation was actually Vx minus c, and what sorry, minus v. This is the relation that we have seen in the last class. And if we just go back here, we're seeing that this Earth is moving with a velocity v. And what is Vx? Vx is nothing but the speed of light that we are analyzing. What is the speed of light along the x-axis? Okay, so what we can write down here is, in place of Vx, we can write it down as c minus v. So understand this. Okay, this is important. We have the speed of light c, and then we have got the Earth, which is also moving with a velocity v. So the effective velocity would be nothing but this, or maybe this is higher, so this minus this, that's the effective velocity, right? That is what is the relativity idea is, or relative velocity idea is, which you might have already done. Okay, next. Now the light is basically traveling from this side to this side. So from here to here, it's traveling in this particular direction. The Earth is also moving in this particular direction, and the light is also traveling in this particular direction. Okay, so the question is, where was this setup done? This was done on the surface of the Earth. So you have the ether medium which is there in the Earth, and the Earth is also having its own velocity. So both these velocities were combined to understand this. Okay, so what was done was, this light is moving in this direction, and the Earth is also moving in this direction. So what we can do now is, we can find out what is the time that was actually taken for the light to travel, that's denoted by T1A, from here to here. Okay, please look into this, from here to here, and that would be nothing but distance. So how much distance it covers is L, that is the distance L, divided by velocity. So velocity for us in this particular case is c minus v. Please remember, we are observing it on the Earth, so we are going to talk about Vx prime. So Vx prime is c minus v. So I will just write it down for c minus v. Okay, so maybe I can just mark this as 1, mark this side as 0.2 and mark this side as 0.3. Okay, so that means time, this is the time from 1 to 2. Okay, so I think it's not complicated here. Now what happens is it was calculated for the opposite direction. So what happens in the opposite direction? Because the light after reflection will try to travel in the opposite direction. So I will just write it down as in opposite direction. That means the light will travel from 2 to 1 now. Okay, so in the opposite direction you have to understand this, that Vx prime is equal to, now the speed of light was calculated in this direction to be positive, so if it is traveling in the opposite direction, this speed will actually become minus c. This will remain as minus v because this is earth is still moving in this direction. Okay, the direction is not reversed for the earth, so this will remain as minus v. So what I can have is effectively this is minus of c, minus can be taken outside, and c plus v. Okay, so that's the velocity in the opposite direction. So if now I want to measure t, so that means I can measure it. So let's say t1v. Okay, the magnitude of this is, the magnitude is distance L divided by velocity. The velocity is c plus v now. This minus will only give me the direction, but I'm interested to find out the time. So I'll just take the magnitude here. So this is c plus v. So that's basically the time from 2 to 1. Okay, understand this. This is just like a story unfolding and why we reach to the point that the speed of light will be the same in our medium. Okay, so what we can do now is we can find out the total time. So how much time did the light travel from the glass plate to the mirror, and came back? Okay, how much time did it take? And that is basically mentioned as the total time. So what we can say is, hence total time T1 is equal to T1A plus T1B. So we're just going to add them up. Okay, and if we do that, I don't think it's a simple algebra. Okay, divided by C minus V plus L divided by C plus V. So we can take the LCM. Okay, so this will be CL VL minus plus CVP. So this L will actually get twice. Okay, so we can just do that. Okay, you can just try doing it. This would be 2L, and at the denominator it would be A plus B into A minus B. So this would be C square minus V square, right? C square minus V square. So what we can do is we can take C. Okay, C here. Okay, so if we just simplify
Sir,
things. Okay, yeah,
sir, C should be multiplied upward, no?
yeah, 2C should be multiplied plus, right? This is 2LC divided by this. Okay, so LC divided by C square. Okay, good. In case I'm doing any kind of error, please check. You also do your maths. And C square can be taken outside, so this will be 1 minus of V square divided by C square. Okay, so if you do that, we can cancel this out. So we basically have the relation as 2L divided by C into 1 divided by 1 minus V square divided by C square. So let's keep this relation in store. And what does this relation tell me? It tells me the time, okay, that the light travels, from traveling from here to 1 to 2 and then back to 1. What is the total time that is being taken? Okay. Now let's check for mirror 2. Okay. Now let's check for mirror 2. Now for mirror 2, it's interesting because you see that the earth is moving. Okay, the earth is moving with a velocity v in this direction, not an issue. But then we don't have any kind of component on the earth, because the earth is moving in this direction. We don't have any component along the y direction. Okay, so we have to consider that. That's important. So what I'm going to do is we are going to take back for the second case. So maybe I can write down the second case, or the second mirror maybe. Here what we have is Vx prime is equal to Vx minus V. Now, you know, the light that is moving might have a y component, x component, but you know, this will be 0. This prime coordinate will be 0, Vx minus V. What's the reason? Because we are talking about a motion along the y-axis, and we know that the earth is moving only along the x-axis. So this component will more or less be 0, okay? And we're going to just, it's still not concluded, we're going to do something here. Vx is equal to V. So here we can say that Vx and V will more or less be equal. This is just mathematical, okay? So what is this Vx? This is the x component. Okay, although we have explained it, but let me just write it down in the ether frame. In the ether frame. On the earth frame, we don't have the x component, but on the ether frame, we do have the x component. Okay, so for this, we have no x component. Therefore, this Vx prime is equal to 0. Vx prime will actually become 0. Okay. Next, since we are talking about the x component, we should also talk about the y component, right? So y component means it's there. Okay, we can just write it down maybe. Okay, also Vy prime is equal to Vy, and that's from Galilean transformation. Vz prime is equal to Vz. Okay, but then, you know, since we are talking about, I'll just explain this again and I'll remove this Vz. We are talking about a motion along the plane. So we have the motion along this, it's going along this, but no ray of light, okay, is coming out of the plane or into the plane of the paper, and that's the reason that considering the z component is meaningless. So if you are confused, don't be, because we are considering the experiment which is being considered only in a plane, so it's only happening in the xy plane, so that's why we are not going to consider the z component. Okay, so Vy prime is equal to Vy, it simply means that Vy is equal to Vy prime. Why I am doing that? Because, you know, this is one relation, this is, let's say, A, and this is one more relation, let's say B. We can square and add on both sides, so what we can do is, okay, squaring and adding, we have it as Vx square plus Vy square is equal to, this side we have got V square plus Vy prime square. Okay, so let's just do this first and then we will understand what is happening here. So, you know, what is this Vx square and Vy square? So if we are considering that the speed of light has got a y component and an x component, and if we square both of them and add them up vectorially, this is actually representing the speed of light. Okay, so this is actually the magnitude of the speed of light. So this particular term on the left hand side is the magnitude of speed of, okay, ether frame, speed of c or light maybe in ether frame. So this is important. So, you know, speed of light in ether frame, we are considering it to be c. So that means this can simply be written as c square is equal to v square plus Vy prime square. We can use logic here, but at the same time we see that mathematically also this is coming out to be something like this. So we have found out what is this relation. Okay, we have found out a relation here. Now we can actually go back to that mirror image and again calculate the time. So let's say I will measure t for the second mirror, and let me just denote it with a. That means it is traveling upwards. This will be actually distance divided by velocity. Okay, this will be distance divided by velocity. So this is L divided by velocity. Now velocity in what? Velocity along the, you know, y prime frame. So this is Vy dash, because it's moving along the y axis. So from this particular relation, what is my Vy dash? Y dash is equal to root over of c square minus v square. So I can just simply write it down to be L divided by root over c square minus v square. So what I'm doing here is this. I'm saying what is the time taken from 1 to 3. Now if I want to find out what is the time taken from 1 to 3, I need to know the distance, which is again L, and I need to know, okay, what is the velocity. So we have just found out the velocity using this calculation, and we have found out that this is the velocity along the y direction in the earth frame or the prime frame. So we have put up this particular relation. So that means this 2a is time from 1 to 3. Okay. Similarly, what we can do is we can also find out the other time, and then we can actually do the total time. Okay. So let's say I have got T2b, T2b. Now because of this relation, T2b, okay, we have it as, again L divided by, now this time, even if you consider the speed to be reversed in the opposite direction, even if you take minus c, there is a c square term, so nothing is going to change. We can just simply write it down as root over of c square minus v square, so this will remain the same. Okay, so mathematically we have to check that. Okay, so this is your time from 3 to 1, so that's the time that we have. Okay, now what I'm going to do is I'm going to find out what is the total time. Okay, so I'm going to find out what is the total time. So therefore total time, okay, maybe we can just denote it like T2. So previously I think whatever I've taken the total time, we have taken it here, total time I've denoted it as T1, right? So I'll take this total time to be T2, and this time actually we can calculate it. So this both quantities are same, so I can just simply write it down as 2L divided by, so if you add them up, okay, we have got this as root over of 1 minus v square by c square, or maybe I'll take one more step here so that you're not confused. So both these quantities are same, right? So I'm just adding them up, so it will be twice of L of c square minus v square, and then this c square I can take common and take it outside. Okay, so I will have it as 2L divided by c square out of the root into 1 divided by root over of 1 minus v square by c square. So that's my T2. So if you observe the previous relation for T1, if you have written it in your copy, you can also check, but check the screen now. T1 is equal to 2L divided by c, 1 minus v square by c square, and T2 is 2L divided by c, that remains the same, but this time it is 1 divided by root over of 1 minus v square by c square. So what does it mean? That there is a difference in time from the mirror 1 and mirror 2. See, mathematically it tells me that there is a difference in time. Okay, so this difference in time we can actually calculate. Okay, so what we can say now is, therefore this difference in time, which is written as, let's say, delta t, is equal to t1 minus t2. So that will be the difference in time. Okay, and depending on how is the difference varying, we will actually get the fringe pattern. Okay, so this value would be 2L divided by c into 1 divided by 1 minus v square by c square, that's your T1, minus 1 divided by 1 minus root over is there v square divided by c square. Okay, now let me tell you something. When you initially saw this image and I told you that this distance is L and this distance is also L, your instinct might have told you that both the times will be same. But when we have done the calculation, we have seen that both the times are not same. There is this root over coming in, which actually creates the difference. Okay. Now why does that happen? Because we are saying that the earth is moving only along the x-axis and there is no motion along the y-axis, as a result of which this particular component changes, because of which we are having two different values of T1 and T2. What does it mean? That the time that the light reaches this point after reflection are different in both the cases. So that means there will be some kind of phase difference. And as per Young's double slit experiment, okay, this is very important. If you have given any kind of entrance exam, if you studied your class 12 syllabus for giving your board exams, you definitely must have studied that. Okay, that is a very important question. Descriptive questions are there from there. So from there you do understand that if there is a difference in time of travel of these light waves, the chances are that you are going to get a fringe pattern if you look through the telescope. So until now, everything is more or less simple, and we do understand, okay, this is what is going to happen. Okay. So what I'm going to do now is, again, I'm going to, do some kind of explanation, which will again be very important. Okay. So let's just write down some sentences, okay, so that you understand it better. Okay. So what does this conclude? Okay. So we have a difference now. Okay. So because of this difference in time, okay, of the rays reaching the telescope, it shows a fringe pattern. Okay, it's very important. It, okay, shows a fringe pattern. So this is something which you should already know, so we are not going to explain that much. Okay. Now, what was the genius thing that was actually done by Michelson and Morley? Okay, because of which they were able to prove the existence of speed of light. Okay, so what they did is, this entire setup was actually floated on a mercury. Okay, mercury is basically is very dense. So this entire setup was actually floated on mercury. So what was done was, okay, if you are going to explain this, you have to write down these sentences. The entire system was floated on mercury, okay, by Michelson. So Michelson actually floated the entire system on mercury, and then what happened was, the setup was rotated by 90 degree. Okay, that is what was done later. Now the entire setup was rotated by 90 degree. Okay, so what happened was, if it was rotated by 90 degree, that means the scales and everything changed, right? So that means you have to again measure the time. Okay, and again the time difference was measured. So what will be the time difference now? So we can actually find out the new time difference. So new time, अभी नया time difference क्या है? See, this was the time when it was in this particular position. ठीक है? Now it was rotated. That means if I just write it so that you can imagine this easily. I'm not going to draw the image again. So this is rotated by 90 degree. Let's imagine this is rotated in this direction by 90 degree. This direction by 90 degree. Then this M1 will come here, and this M2 will come here. Now, if you just do the maths, you see that whatever time was actually given by M1 will now be given by M2, because M1 has shifted from the, along the axis to perpendicular axis, and M2 has shifted from the perpendicular axis to the parallel axis. So whatever time was given by this will be given by this now, and whatever time was given by this will be given by M1 now. Okay, so we are going to see that. So we are not going to do the calculation. I think this is logical. So that means whatever relation we are having here, we are going to have a similar relation now. So that means the time difference, let's say delta T star, okay, is equal to 2L by C. That will remain. We are just considering the magnitude, remember. And this would be, it will just get reversed. That's it. That's the change we have. 1 divided by root over of 1 minus v square divided by c square, minus 1 divided by 1 minus v square by c square. So if it is rotated by 90 degree, this time gets reversed. Okay, now what we can do is, we can also calculate this difference. Okay, so this difference can also be calculated. So hence, okay, the change can be calculated. Change can be calculated. Change of what? Change of time can be calculated when the entire setup is rotated. And what is that change? This is nothing but delta t minus delta t star. Okay. Now the point here is that if this delta t uh, is and delta t star, there is a change, then there will be a shift in the fringe pattern also. That's logical, right? You have the fringe pattern because of delta t. You have the fringe pattern because of this. If you are changing the entire system setup and that time difference also changes, it means that the fringe pattern should also shift. Okay, let me just put it in sentences, okay, so that you can understand it better. So what we have here is this. Okay, let me just write down a few things here. So this is important. Okay, let's just note this down. The fringe pattern, okay, fringe pattern is because of delta t. Okay, so I just write down t here, put the delta later. Okay, this fringe pattern is because of delta t. That we know now, it's clear, because we know Young's double slit experiment. We know if there is a difference in time, there will be a fringe pattern. So this fringe pattern is because of delta t. So what happens is, now if, okay, this delta t star, so we have got another term now, delta t star. Okay, now if this delta t star is different, okay, what happens is the fringe pattern will shift. The fringe pattern will shift. How do you measure the shift? See, this is something which I'll explain to you verbally. You must have used, in your lab, or maybe you might have seen some videos. You can check YouTube also. Whenever there is any kind of experiment which is happening, maybe in a dark room, you're observing a fringe pattern or a diffraction pattern. You basically use a telescope, and a telescope has got a crosswire attached to it. Okay, if you've done bio in your class 11 12, you might have seen those cross sections and all. So there is always this crosswire. So you can use that crosswire to know whether a fringe has been shifted or not. In this particular case, when we are actually rotating the entire system, if there is a shift in fringe pattern, it might be smallest of changes. Okay, it might be very difficult to detect it with our naked eye. We have to be very careful while detecting this shift pattern. That can be detected. Okay, how? Because Michelson and Morley has set up the experiment in such a way that even if there is slightest of change, they could detect that. Okay, so if there is slightest of change in T star, there will be a shift in the fringe pattern. Okay, so the fringe pattern will shift. And what happens now is, I will tell you this relation. Delta T, I already know. Delta T star, I already know. L is something which is based on the experiment. So I know what is L. I know what is the speed of light in ether, 3 into 10 to the power 8 meter per second. The only thing that I don't know is the velocity. So that means if I take this relation, okay, and put these results on this side, I will have everything known, because delta t minus delta t star can also be calculated. How? By knowing the shift in the fringe pattern. If we know the shift in the fringe pattern, we know what is delta t minus delta t star. We know that. Secondly, on the on the right hand side, we will know what is L, we know what is C. The only thing that we need to calculate is V. So we have one relation from here. There is only one unknown, which is the velocity. And what is this V? V is the velocity of light on Earth. That is what we are measuring. So using this relation, we can find out what was the velocity of light on Earth. Okay, so this was the idea which Michelson and Morley developed. Okay, so the thing is, the shift in the fringe pattern. Okay, maybe I can just write down this delta. Delta हो गया, ये भी delta हो गया. It's different. Then the fringe pattern will actually shift. Okay, so this delta t minus delta t star, okay, this delta t minus delta t star can actually be used now. Okay, we can actually use this delta t minus delta t star for what? We can actually use them, can be used to calculate V. So I hope you understand how did we calculate, because we already know delta t minus delta t star. How? We know it experimentally. There is a shift in the pattern, fringe pattern. That means we can calculate delta t minus delta t star from there. Okay, and then we know what is L, what is C, we can put it into the result, we can easily find out what is V. Okay, and what is this V? This V is nothing but velocity, okay, of ether in earth stream. Okay, so we basically have the speed which is actually getting measured, so we can actually do it. So that was, the idea. That was something which should have happened. Okay, there will be a velocity. Now it's very simple. The idea is simple here, that now if the speed was different in the Earth's frame, this V should give me a result and I should actually get an answer. Okay, but it was observed that this delta T minus delta T star actually gave no fringe shift. There was no fringe shift at all. There was no shift in the fringe pattern. Okay, we have rotated the entire system, still the time difference more or less remained the same. There was no fringe shift. If there was no fringe shift, the final result that came out was that the velocity was zero, which is actually a null experiment because it didn't give me a result. Velocity can't be zero. It was a null experiment which did not give me a result, because of which it was concluded that the velocity of light should be same in all the medium. Okay, how do I write down this? Okay, but after experiment, it was observed, okay, that there was no fringe pattern shift. So there was no shift in fringe pattern, and V, okay, or V is equal to 0. Okay, and this is also interesting that it might happen, because if I actually, let's say, draw a circle, maybe, or maybe the Earth, okay, the Earth is also having its own motion. We know that Earth is not at rest, it is in motion. Okay, and I can measure, and let's say I was talking about the Earth moving in this direction. So if you look into the vectorial representation and all, in this particular time, the Earth is rotating around the Sun, and we are measuring the speed at this point of time of the year. Now at some point the Earth will be here, and they also did the calculation at this point, where the velocity will be in a different direction. They also did it here, and they checked for this also, but at all points the result was actually coming out to be 0. So that means in any time of the year the velocity was always 0. That means it doesn't even depend on time also, or at what position the Earth is, the speed of light will remain the same. Why they did it at different points? Because they wanted to know that at different positions of the Earth's motion, will the velocity remain same, or it is only during that particular period. It was observed that it is 0 at all point of time. Okay, so they have done it a very long experiment. It's not the only thing. So that means, that's why I'm writing it in bracket. V is equal to 0 in any time of the year. In any time of the year, it was observed that V will actually remain as 0. Okay, so the concluding lines for this, there's a lot of theory here. This was the null experiment of Michelson Morley. So this was the null experiment of Michelson Morley. Why null? Because it didn't give me a result which they were expecting. It didn't give a result which they were expecting, and that's the reason that this is actually going to give you the idea that the speed of light is not going to change. It's not changing anywhere. Okay, so imagine if this was true, okay, and V was actually not 0, this entire special theory of relativity would have failed. Okay, that means that the speed of light would have been C only in the ether frame and no other frames of reference. Okay, and this would have failed the special theory of relativity idea. Okay, because we are going to understand what is the postulates of speed of light. Okay, so that's the reason we're going to check that. So we are going to check more on this later in the next class. Okay, therefore we can conclude speed of light is C in all inertial phase. Okay, and from here we are going to write down the postulates of special theory of relativity, where we actually say that the speed of light is vacuum is this will be same in any kind of medium, okay, regardless of the motion of the observer or the source. That's a very important conclusion of special theory of relativity. So this is what was the conclusion of Michelson Morley experiment. Let's just do a very quick revision here. What it was done that uh, they have actually made this setup and they have measured what was the time of light going from here to here and then coming back. Okay, and then it was also measured what was the time from going here to here and coming back, and then both of them was observed that there was a time difference. Okay, and if that ray is observed, the combination of these two rays are observed through a telescope, a fringe pattern was seen. So a fringe pattern was observed. That is was simple. Okay. So once the fringe pattern was observed, it was the entire setup was actually put on Mercury or floated on Mercury. So if it was floated on Mercury, it means that you can rotate it easily because Mercury has got a very high density. And then what happened was it was rotated by 90 degree, and then again the experiment was performed, and then delta T star was calculated. So it just interchanged the values of T1 and T2, and then the difference can be calculated easily. Now, if we look at this relation of delta T minus delta T star, everything is known. Delta T minus delta T star can be calculated by the shift in the fringe pattern, and C is known, L is known. But then it was observed that there was no shift in the fringe pattern. That means the result for V was coming out to be 0. Now this experiment was actually conducted at different times of the year, so that the motion of the earth may be in different direction, and every time it was seen that the velocity v came out to be 0. That means this Michelson-Morley experiment which was performed was a null experiment, getting no output. So this simply concluded that the speed of light will be c in any inertial frame that we are considering. So it's very important to know this, that it is in the inertial frame. We're not talking about a non-inertial frame. Okay. So there might be still possibilities if you are looking into a non-inertial system, which is it's a chaos, it's a chaotic system. Okay, it's we are moving with a very high speed or very high acceleration. There the chances are might be the speed of light will be different. But then in inertial frame, okay, because this was an example of an inertial frame, the speed of light will more or less remain the same. Okay.